Now, not all power supplies are that reliable, but it's maintaining the source. Doesn't matter what the source is, whether it's mains connected or whether it's battery operated or what. That reliability needs to be there at all times. Sorry, let me just getting this into view. Okay. Now, stabilized power supplies. Well, broadly speaking, regulated power supplies or stabilized power supplies can be reduced to four main areas. Okay. 1. AC to DC supplies type A. Number 2. DC to DC supplies type B. 3. AC to AC supplies type C. And 4. DC to AC supplies type D. Okay. Type A is used more than any other. The remaining three groups are more specialized. In AC to DC supply systems, the unstabilized power supply is a simple rectifier and smoothing circuit. Now, to have a smoothing circuit, you will need to have a circuit which contains a capacitor, because your capacitor will maintain your supply at a given level. The output from the unstabilized power supply is applied to a controlling device which regulates the voltage to give a steady DC output. A proportion of the output signal is fed back, usually from a resistive type of network, and is compared with a reference signal. The difference between the two signals is then used to activate the controlling element in such a way that it maintains the level of the output at a constant value. Okay. These regulators, which regulate the output voltage current, can be further subdivided into two groups: series regulators, shunt regulators. Okay. Let's look at series regulators first. The controlling device is connected in series with the load, and to regulate the output, it must at all times absorb some of the supply voltage. When the series controlling device is a transistor and is used to control an unstabilized voltage supply of 20 volts, then several volts would need to be dropped across the transistor. This allows the voltage across the transistor to be altered by the feedback signal to accommodate variations in the supply voltage and load resistance. Shunt regulator. The controlling device is in parallel with the load, and to effect output regulation it must pass current at all times. When the current through the controlling device falls to zero, regulating action ceases. Now, in more sophisticated power supplies, protective circuits are built into the network to limit one or more quantities to a safer level. For example, in the event of an excessive overload or a short circuit being applied to a semiconductor voltage regulator, in order that we may protect the semiconductor regulating device, the current must be switched off or reduced to a safe value within within 10 microseconds or within 100 microseconds. Now, the faster you can make your safety device operate, the more protection you will offer to your semiconductor components, because these are highly sensitive to current and voltage. Fuses cannot provide this form of protection, and feedback techniques are used. Okay. The problem is not so serious in regulators using fermionic devices, and a thermal cutout can be used. A feature of semiconductor devices is that when they fail catastrophically, they usually develop an internal short circuit between the collector and emitter. So your transistor would simply break down and would be of no use to you in any shape or form. And that word is when they fail catastrophically. Okay. Now, in series regulators, this means that the unregulated power supply will be directly connected to the output terminals, possibly causing damage to the connected load. One method of protecting the load against this type of fault, known as crowbar voltage protection, employs a sensitive circuit which monitors the output voltage of the regulator. This circuit instantly applies a short circuit to the output terminals whenever the voltage rises above a predetermined level. A thyristor can be used as a crowbar device. An inherent advantage of a shunt voltage regulator in the above case is where the thyristor is used, that a short circuit in the regulating device causes the output voltage to fall to zero instantly. So here, if you have a short circuit occurring, then that simply means that the voltage at the output will simply drop to zero, so therefore it will not damage your components. The reference voltage source in regulator circuits is usually a Zener diode. Okay, Zener diode. And somewhere along the lines in one of my other lessons, you would see me showing you a Zener diode how the voltage it operates. Okay, but that's earlier lessons, so you'll need to look back quite a bit away. A voltage reference source. A popular circuit used as a voltage reference source normally consists of a Zener diode with its cathode connected to the positive pole of the unstabilized power supply via a resistor R. The magnitude of the supply voltage V1 is greater than the Zener diode breakdown voltage Vz. Now, please take note, because you'll need to follow this for yourselves directly. Because I've wrote this myself, I know where I'm going with it, so I may be ahead of you. So please be sure that you take the time to understand what I'm trying to say here, okay? Your style of learning is slightly different to my own, and you have to find that level of style of learning for yourself. As I've told you before, put pen to paper, okay? You cannot go wrong with that. Okay? The magnitude of the supply voltage V1 is greater than the Zener diode breakdown voltage Vz. The potential difference V1 and Vz is equal to V1 minus Vz. This difference appears across resistor R. Zener diodes selected for this purpose should exhibit practically no change in breakdown voltage with temperature. So you need a Zener diode with a high temperature coefficient. Okay, it will not collapse on the temperature with temperature change. The output voltage from this circuit has a value equal to the breakdown voltage of the Zener diode V2 equals Vz. This means the voltage at the output is the same voltage which will appear across the Zener diode. Should the value of the supply voltage V1 alter in value, the PD potential difference across R alters to compensate for the change, and the output voltage remains constant. A simple form of voltage reference source, diagram A1. Okay. Let's just go into it so we can make sure we can get it in full view. Okay. And here you have your rectified and smoothed supply, okay, coming in. Output voltage, okay, your Zener and your Vz, okay. V1 is your input, Vz is the voltage across the Zener diode. That will collapse and break down, not preventing any excess of that voltage being exceeded. So if your Zener diode has a given rated voltage, then that will appear across this point. If it exceeds that, then this will break down to ensure that that output is protected and does not exceed a given value. That is R. Okay. Rectified and smoothed supply, output voltage, a simple form of voltage reference source. Okay. To find the value of R, as in the diagram A1, we need to apply the following procedure. R equals V1 minus Vz over I. Here we have R equals V1 minus Vz. Now, V1 is the applied voltage and Vz is the voltage across the Zener. Where Pz is the power rating of the Zener diode, the circuit ceases to act as a regulator when Iz equals 0, i.e. when the load current is equal to I, the current in the circuit. This occurs when the minimum value of load resistance RL min is connected. You have here RL min equals VZ over V1 minus VZ equals R. Okay. Now again, look at this for yourselves. Make sure that you do a little bit of groundwork and calculation for yourselves. You would be familiar with this. Some of you would have done Zener diodes already. It's one of the things that you will do in electronics. And all electricians are learning electronics as part of a subject which forms part of the course. Okay. Example. Design a voltage reference circuit which uses a 5 volt 400 milliwatt Zener diode. If the supply voltage is 11 volts plus or minus 2 volts, calculate the value of the resistor R, which is to be chosen from a range of preferred resistors with a 10% tolerance. Estimate the lowest value of load resistance which can be connected before the regulator fails to function correctly. Solution. The current I in resistor R is equal to the power of the Zener divided by the Zener voltage, P equals I times V transpose for I. I equals PZ over VZ equals 400 times 10 to the minus 3 over 5 equals 0.08 amps or 80 milliamps. Make sure you have done the calculation for yourselves, okay? That is 10 to the minus 3, okay? It's just the way I've written it. Again, adapt your style of learning that's suited to yourself. Amend that accordingly. When the maximum voltage is applied, the current I through the resistor R must not exceed 80 milliamps. R equals VI max minus VZ over I equals 13 minus 5, 80 times 10 to the minus 3, etc. equals 100 ohms. Okay. The resistor is rated at 10% tolerance, so it has a minimum value of 1090 ohms from its original value of 100 ohms. We therefore have to calculate the current the resistor will pass in reality. I equals V over R. Again, you'll notice that I still use V over R, but remember that you'll be using U over R, okay, in modern day terms. 8 over 90 equals 0.088 amps or 88.89 milliamps, okay. Make sure that I've got this in. Let me just go back a bit. Okay, make sure that I've got this close to angle. Bear with me for a moment. I'm just going to recap, okay? So you can see, make sure I've got everything on my camera. Okay, I'm good, thank you. Now, as 88.89 milliamps exceeds the current we wish to pass, we must look to using a larger resistor, approximately 110 ohms. The series controlling device. The basis of the series regulator is the emitter follower. The signal Vx applied to the base of the transistor is the output from a voltage reference source. The value of the output voltage VO is slightly less than the value of Vx. Since Vx has a constant and stable value, it follows that the output voltage is also constant and stable. And here we have our unregulated DC. Okay, apply voltage from a reference source applied to the base of the transistor. Okay, that's the emitter, and that would be your collector. That is the base. Okay, V out would be your RL is your resistive load. Okay. And this is a NPN transistor, not a PNP, okay? NPN transistor. And here we have similar circuit. The basis of the series regulator is the emitter follower. The signal Vx applied to the base of the transistor is the output from a voltage reference source. Okay. The value of the output voltage Vout is slightly less than the value of Vx. Since Vx has a constant and stable value, it follows that the output voltage is also constant and stable. Okay, this is the work I did, just mentioned earlier, okay, at the top, but I did this in a written format to make sure that it is comprehended, I hope. Okay. And here's what we're looking at basically, okay. This is the input voltage from rectifier or smoothing circuit, okay. This here makes sure that Zener makes sure that that voltage here, whatever appears here, does not exceed the Zener rated voltage. Okay, so whatever appears across the Zener should be appearing across here. If the Zener fails to break down, then to bypass the excess voltage, then you're going to have a problem here. That voltage would be too high, and that could cause damage to your components. Zener diode example number 1. A 5 volt stabilized power supply is required to be produced from a 12 volt DC power supply input source. The maximum power rating PZ of the Zener diode is 2 watts. Using the Zener regulator circuit above, calculate A, the maximum current flowing through the Zener diode, and here is the formulation for that. Okay. We are dividing the power of 2 watts by 5 because the power rating of the Zener is 2 watts, which would be given in the catalog of specifications. The 5 volts come from the voltage we require at the output, and it is the voltage which the Zener will need to maintain from the 12 volt rail supply. So, to calculate the resistor, we will need to calculate the resistor, we must subtract Vz from Vs This is 12 volts. This is given in the question. We have been told that the stabilized power supply is to be 5 volts, therefore 12 minus 5 equals 7 volts. The minimum value of the series resistor RS is going to be 17.5 ohms. Again, apply your calculations, do it for yourself, put pen to paper, don't just try to read it off the screen. It's not your work, this is my work. You need to create your own work from the information given. Okay? To complete this, we would have 7 divided by 0.4 or 400 times 10 to the minus 3, which gives us the answer of 17.5 ohms. The load current IL, if a load resistor of 1K is connected across the Zener diode, then we will have a current of 5 milliamps, and here is your result to that. Okay, again, apply it for yourselves. Okay, do the calculations. Okay. And here's our framework. Okay, symbol, cathode, anode. Okay, now the current for the Zener diode, it will be forward biased and it will operate within the given from 0.3 to 0.7 volts. If it exceeds 0.7 volts, it collapses and breaks down and drops and triggers the breakdown of the Zener. Okay, and that is what you want the Zener to do, to be able to effective to control and maintain a constant output supply, which provides you and protects your circuit. Okay, thank you. I hope you found this useful. Let me just make my way up slowly so I can recap and make sure that I have everything in view. Okay. I hope you have found this useful. Okay, again, you need to look at the video on, let me just get to it 1 second, bear with me. Okay. Make sure, because I don't want to give any variations to what I've just said, you see. Okay, so I'm going for this now, making sure that we can see it fully on the screen. Or you can stop it or pause it at given points if you choose to. Okay. Okay, and here we are. And again, you need to look at stabilized power supplies in regards to this video. Okay, thank you again. I hope you found this useful. Okay, bye bye for now.